And now we will consider how bond length and energy relate to each other. All right, so when I look at bond length, I'm looking at the optimum distance between two nuclei in a covalent bond. So basically, we have too close together, and that's not going to work. Too far apart, and there's just not enough attraction for the bond to actually form. And so there's an optimal distance between the two nuclei. And so, when we look at it, if I've got a nucleus and then, my valence electrons and a nucleus and my valence electrons. What I'm looking at with my bond length is I'm looking at the distance between those two nuclei. All right, so it's not the distance between what's happening on the valence electrons, but it's actually the distance between the two nuclei. That's how we measure our bond distance. Now, when I look at bond dissociation energy, okay, this is considered to be our bond strength. Now, there's two ways of looking at this. Okay, we can look at this under the understanding of how much energy it takes to break a bond or how much energy we get when we form a bond. Okay, so our bond strength or our bond dissociation energy can be that amount of energy required to break a bond. Okay, or it can be the amount of energy that we get when the bond forms. So breaking a bond costs energy. We have to, input energy in order to get the bond to break. But forming a bond, we get energy back from that. Okay, and then when we look at all these different bond energies, we have this correlation between the bond length and the bond strength. So if I look at my carbon-carbon bonds, a single, a double, and a triple bond, all right? My single bond has an energy of 347 kilojoules per mole, whereas my bond length is 154 picometers. When I go to my carbon-carbon triple bond, my bond length drops to 120, so they're closer together. And now my bond energy jumps to 837. All right, and so the closer together we are, the more energy associated in the bond. So as the bond length decreases, the bond strength increases. Okay, so closer together, higher bond strength. All right, and then one last consideration to start thinking about are things called sigma bonds and pi bonds. So to have a molecule, we have to have sigma bonds. It's the first bond that forms between any two atoms. Okay, the pi bonds are the second and third bonds to form above and below the plane. So if I look at something like, this nitrogen here, I have a triple bond. So I have one sigma bond and two pi bonds. If I look at oxygen molecule here, I have one sigma bond and one pi bond. And hydrogen, I just have one sigma bond. Because we know when we start assessing geometry, okay, we know that a single bond or a double bond or a triple bond is considered one region of electron density. Well, this is because when we look at geometry, what we're considering are things with the single bonds. So if we look at like this structure right here, okay, I have two carbon-hydrogen sigma bonds, one carbon-oxygen sigma bond, and then a carbon-oxygen pi bond. But I have three total sigma bonds. I have three regions of electron density around my central atom, so that's where I get trigonoplanar from. And so understanding the difference between sigma and pi bonds helps us with our geometry, because the geometry is dictated initially by the sigma bonds that form. Okay, so there's some definitions to think about and get in your head, because those will be coming up in greater detail. We'll start considering this even further. All right, so that ends all of this stuff.